In today's class, we will look at Hessian and its role in online learning. Why do we need Hessian? Because so far in the backpropagation learning, we are focused on first order derivative. First order derivative is a gradient of the error surface used to decide the direction of the weight updates. However, we observe that learning is fast in some cases and very slow in others. Learning may oscillate or become unstable. Lower layers learn slowly compared to upper layers. Now, these behaviors cannot be explained by the gradients alone. To understand them, we should study the second order structure of the error surface, that is the Hessian matrix. Let the average cost or the error function be given by EAV of W, where W is the weight vector of the neural network. Hessian matrix is the second order partial derivatives of the error function with respect to the weights. If we have M weights, the Hessian matrix will be M cross M. That is, first row will be the second order partial derivative of W1 with respect to W1, and second column in the first row will be the second order partial derivative of the error of the weight function W1 with respect to the weight 2, and it keeps going until all the weights are covered. Similarly, the second row will be the second order partial derivative of W2 with respect to 1, and then W2 with 2, and W2 with W3. The interpretation is the Hessian is a square matrix of the second order partial derivatives. This captures the curvature of the error surface. That is, Hessian matrix, which is going to have a second order partial derivatives, will capture the curvature of the error surfaces. Each element tells us how fast the gradient itself changes. Gradient tells us where to go, but Hessian tells us how the surface bends. That's why we need the Hessian matrix. The role of Hessian in neural network learning. Hessian plays an important role in neural network, especially in backpropagation learning dynamics, stability of learning, speed of convergence. The eigenstructure of the Hessian strongly influences the learning behavior in the backpropagation. Eigenvalues of the Hessian. Let the eigenvalues of the Hessian matrix be lambda 1, lambda 2 up to lambda m. Why eigenvalues matter is each eigenvalue corresponds to curvature along a particular direction in weight space. Different curvatures, different learning speeds along different directions. Typical eigenvalue composition in multilayer perceptrons. For a multilayer perceptron trained using backpropagation, experiments have shown that the Hessian has small number of small eigenvalues, large number of medium-sized eigenvalues, small number of large eigenvalues. The factors affecting Hessian eigenvalues are non-zero mean input are the output signals. If inputs are induced neural outputs have non-zero mean, Hessian eigenvalues are spread increases, learning becomes slower and more unstable. That is, if the input signals are non-zero mean, eigenvalues spread increases. Because of this, the learning becomes slower and more unstable. Therefore, we have to avoid non-zero mean input signals. Here it is with respect to non-zero mean input signals, not the output signals. That is, in the neural networks, we should avoid the non-zero mean input signals. Next, we will look at the correlation between the input vectors and the output vectors. That is, high correlation between the input vector elements, in the sense, for example, say we have two features which are the input vectors for the neural network model. One input feature vector is Celsius and the other input vector is a temperature in Fahrenheit. Both are the input vectors are the features, but both are correlated, because if I know Celsius, I can know what is Fahrenheit value, or if I know Fahrenheit, it can give the Celsius. We are going to tell that there is a high correlation between the input vectors if one input can be predicted from the other. What is the meaning of high correlation between the neurons output? That is, if two hidden neurons learning the same feature, then they are going to produce the same output. That is, we should avoid the inputs, high correlated input vectors and high correlation between the output neurons, because this will lead to ill-conditioned Hessian and slow convergence of the algorithm. Next is layer-wise variations in second-order derivatives. Second-order derivatives are smaller in lower layers, larger in higher layers. The weights in the first hidden layer learning slowly. If there is smaller second-order derivatives in the lower layer, learning will become slower. Weights in the last layer learn faster. If there are larger second-order derivatives in the higher layer, the learning is going to become faster. That is, these are the factors which will affect the Hessian eigenvalues. As said, we have to avoid the non-zero mean inputs, because as said, in online learning, the speed of learning depends on the Hessian matrix. The important quantity is the condition number. Condition number is calculated by lambda max divided by lambda of min, where lambda max is the largest eigenvalue of the Hessian and lambda min is the smallest non-zero eigenvalue. This condition number is nothing but the learning rate, which is proportional to the lambda max divided by lambda min, the maximum eigenvalue and the minimum eigenvalue. The effect of the non-zero mean inputs is, if the input signals have non-zero mean input, this ratio is going to become large. That is, learning time is proportional to this ratio. And now if the inputs are non-zero mean inputs, this value will become large. The error surface will become ill-conditioned. Learning becomes slow and unstable. It will be very slow and unstable. That is what we are trying to understand as if the inputs are non-zero mean inputs, this ratio will be very large. This ratio is proportional to the learning time, because of which the error surface will be ill-conditioned and learning becomes slow and unstable. That is, to minimize the learning time, that is to learn the updated weights properly to predict the output, non-zero mean inputs should be avoided. Next, how to avoid the non-zero mean input signals in the neural network. If the input features are indicated by x, xi, then to make it a mean zero input signals, subtract each input vector xi with respect to the mean actually. That is, this ensures mean inputs are achieved. That is, if I make my input features subtracted from the mean, it becomes a zero mean inputs, which will improve the Hessian eigenvalue spread and speeds of the learning, because we want the spread of the Hessian eigenvalues to be proper, and if it becomes proper, then the speed of learning will also be increased. But this we can make a zero mean input from the input layer, but what is the problem with the hidden layers? That is, how to make it a zero mean inputs, because we will get the from the input layer, it goes to the hidden layer, and then we can have one more hidden layer, and then after that the output layer, or many more hidden layers. Now here we should get the non-zero mean, that is zero mean inputs, because one input of the hidden layer is getting propagated, output of the hidden layer is getting propagated as an input to the other hidden layer. And now how to make this as a zero mean input signals? That is, we cannot manually subtract the mean inside the hidden layer, because this is not in our control. This input is coming from the training set, but here internal calculations are happening. Now when we have to get zero mean inputs here. One solution is we have to use the appropriate activation functions in the hidden layers. That is, if we use tan h, then it will give the range in the range of -1 to 1, and mean will be approximately equal to 0, so that we will get a good spread of the Haykin values, and then faster learning will happen. But if it is a sigmoid, mean once again becomes non-zero and slow learning will happen. That is, the takeaway is zero mean signals better Hessian, faster learning. Non-zero mean signals poor Hessian and slow learning. Next, we will understand the asymptotic behavior of online learning. Asymptotic behavior refers to the behavior of the learning process after a very large number of iterations. That is, when n tends to infinity, we start with first iteration and second iteration, and it keeps going on. And when n is very large, when the number of iterations are very large, then what is the asymptotic behavior? What is the behavior of the learning process? That is, understanding the behavior of the learning process for the large number of iterations we are going to refer to as asymptotic behavior. In simple terms, what happens to weights after a long training? Because we keep updating, then what is going to happen? Do they converge? Whether we will we'll find the optimal weights, or do they fluctuate? That is, we will keep training. Sometimes we may get a good weights, but after that the weights will be updated, and that may increase the error instead of decreasing the error. That fluctuations will happen. How stable is the learning? Because why we have to study the asymptotic behavior is we have to look at this 4 questions. That is, what happens to the weights after long training? Do they converge? Do they fluctuate? How stable is the learning? In online learning, the network weights are updated one sample at a time. We know that. We have seen in the difference between the batch learning and then the online learning. And the learning is stochastic, randomness, because we are getting one sample at a time, or sometimes we from a given set of n examples, 1 2 up to n after n training, we may draw randomly one at a time, and then we keep updating the weights. Sometimes in the online learning, the errors may not decrease smoothly. To understand such learning, we study how the average learning curve behaves over a long period of time. That is, asymptotic behavior of online learning is to study the average learning curve of the neural network, how it behaves over a long period of time, for many number of iterations, how it behaves. In online learning, the weights are updated one sample at a time. That is what we have seen. So the learning is stochastic, because we draw the samples from a given n training samples. We draw samples, any one sample at a time, and do it. Therefore, it is stochastic. Because of this randomness, even after a very long time, the weights don't settle exactly at the minimum. They may fluctuate around it. The long-term behavior of the weights is what we call asymptotic behavior. If the weights are fluctuating, what controls or how large these fluctuations are? The answer is the learning rate. That is, if the weights are fluctuating, what controls how the large these fluctuations are? That can be looked at by looking at the learning rate. To ensure the stable learning, the learning rate always should be less than 1 minus lambda max. Lambda max is the largest eigenvalue of the Hessian matrix. If the learning rate parameter is too large, learning becomes unstable. Weights may diverge. This also should not be large. Therefore, here we can look at in the table, that is, for a large learning rate, convergence will become fast, but fluctuations will happen. It will be large. Small learning rate, convergence speed is slow, but fluctuations are also slow actually. Therefore, we have to always balance the learning rate value and small, but too small is also not good. But if the small learning rates are being taken, convergence is slow but fluctuations are also very less or small.